Okay, looks like we're live. Let me just check the YouTube. Okay, YouTube is live as well. Cool. Okay, today we'll be going over index and staging buffers. I'm not really sure what that is exactly, but we'll learn today. So let's get into it.
Triangles, in which case we must duplicate that vertice's data. For example, take the simple cube we have been rendering for the past few tutorials.
Let's change the default speed to 2. Um,
Even though a cube has only 8 unique vertex positions, each face of the cube contains 2 triangles, so 6 vertices,
yeah,
and therefore is using
set
36
to
vertices to be rendered. A vertex currently consists of 2 3-component vectors, one for position and another for color. As we continue to add more attributes to each vertex, such as normals, texture coordinates, and tangent vectors, the number of attributes and the size of each vertex will only get larger. For most models, it just doesn't make sense to be duplicating this data, and that's where index buffers come in. An index buffer is a piece of additional data we can provide to the model's draw command that tells the GPU how to combine vertices to make up triangles. An index buffer is like an array of pointers into
interesting. Okay, vertex buffer makes sense as an array of the vertexes. Index buffer, okay, so array of the triangles, yes.
the vertex buffer. The first 3 index values say which 3 vertices make up the first triangle.
Could be like a 3 by like an array of 3 by 1 arrays.
The next 3 vertices for the second triangle, and so on. This way, the vertex can contain only the unique vertex values. And to reuse a vertex, we simply use its index multiple times within the index buffer. Let's start with the most basic example, a rectangle consisting of 2 triangles. Using our previous method, we would require a total of 6 vertices in the vertex buffer, 3 for the first triangle, and another 3 for the second, and we've had to duplicate these 2 vertices. Using an index buffer, we specify each unique vertex just once within the vertex buffer, and the index buffer will say how to link up these vertices into triangles. So for the first triangle, we would have index 0, 1, and 2, and then 2, 1, and 3 for the second triangle. For complex 3D models with many attributes per vertex and triangles sharing many vertices, the amount of GPU memory saved with the use of an index buffer will quickly add up. Okay, let's get to coding. Start by opening the model header file, and below the vertex
Okay. Model header file. Let's close these other ones. And still
called builder, which will contain 2 vectors. The first will contain vertex objects called vertices and initialize it to be empty. The second std vector will contain values with a uint32 type called indices and also initialize that to be empty. This builder will be used as a temporary helper object, storing our vertex and index information until it can be copied over into the model's vertex and index buffer memory. Okay, next.
let's make this struct builder steady effect vertex vertices steady vector event 30 indices. And
LVE model builder reference as the
const LVE model builder below is
vertices.
this.
Also needs to create an index buffer. So I'm going to first duplicate the create vertex buffers function and rename it to be create index buffer. Update the function
Area on shelf. Control D. Create index buffer. And so we use int. And so we indices.
vector of uint32 types and rename the parameter to be indices. Then duplicate these 3 lines. We similarly require a vk buffer, device memory, and count for
Control C, Control index. Control V.
rename the variables to index buffer memory, and index count. Finally, I will also add a member variable with type bool called has index buffer and initialize that to false. This way we can have both options.
Bool as index buffer equal false. I did this at reset over there. Hmm. I'll just change some chat settings. Let me just update the chat box. Okay. Yeah, it does reset itself. Now I'll just have them disappear after every 30 seconds or so. Okay, let's get back.
Available to us, creating a model with just vertices as we've been doing so far, and alternatively a model with both a vertex and index buffer. Okay, now navigate to your model implementation, and we will start by updating the constructor. Change the second argument of the constructor to instead be a const.
Control C, we model we model here. This is for which function? SLV model. Yes. Builder vertices. Yes, we'll also create the index buffer builder dot indices.
Called builder, and then update the create vertex buffers function with builder.vertices for the argument. Then just below call create index buffers with builder.indices as the function's argument. Inside the destructor, we need to clean up our index buffer in memory, but only if the model contains them. So I will copy these two lines, then add if has index buffer,
In the destructor, minus f as index buffer equals true. Index
update vk destroy buffer to take the index buffer as the second argument, and vk free memory to take index buffer memory. The create index buffer function is very similar to the create vertex buffers function, so I will use that as my starting point. Duplicate the function.
Okay, let's copy. Yes. Create index buffers. Let's copy it. Copy indices. Index index this one is buffer sets into new control F vertex index replace replace vertices indices. Do it. Yeah, that should be fun.
Read create index buffers, and take a const vector reference of uint32 types called indices. Instead of vertex count, we have index count is equal to static cast of indices.size. Following this, we can properly initialize has index buffer to equal index count is greater than 0. So what this means is that if a non-empty vector of
As index buffer equals index count greater than 0.
Rendering the model. Now, we no longer require this assertion, but instead we'll check if not has index buffer, then return. So when an index buffer is not present,
If not has index, then return.
we don't need to do any more work. Okay, the buffer size should be equal to the size of indices at index 0 multiplied by the index count. So update those two spots. And for the create buffer function, we need to change the vk buffer usage from vertex buffer bit
Index buffer bit. Yeah,
visible and host coherent can stay. And the last two arguments can be changed to be index buffer and index buffer memory. All that's left to do is map the memory. Three things need to be updated. We want to vk map memory for the index buffer memory, we want to memcopy the indices.data, and finally unmap the index buffer memory. Let's just quickly review what we did here. This is pretty much exactly
I'm just replacing
that. The purpose of these buffer objects is that we want to write this
index with
information to device
this.
memory. First, we create a buffer of the required size on the GPU with the create buffer command. Then we map memory on our host to the device memory. What this does is create a data region on the host that is linked to the device memory. This way, when we use memcopy to write to the CPU accessible memory, that information will also be flushed to the GPU memory through that link we established. Finally, since our mesh data is unchanging, we no longer need the region of data on the host side, so we can unmap it and let it be cleaned up. So we have created an index buffer, but we need to tell Vulkan how to use it when rendering. In the model draw function, we will check if has index buffer, then use the vk command draw in.
The model draw function. If has index buffer,
This takes a command buffer, the index, and an instance count of 1, and then 0, 0, 0 for the first index, vertex offset, and first instance respectively. Otherwise, if we don't have an index buffer, we just use the regular draw command. So add else vk command draw.
it's yeah. We can command Control C, Control V, index count. One zero zero and one more zero. Command buffer. I'm guessing this is the actual correct one. Command index. Okay, 0.
Just like the normal draw function, but it signals to Vulkan that there will be an index buffer available for use. But we haven't yet made the index buffer available. So in the model's bind function, following the call to bind the vertex buffer, add if has index buffer, then vk command bind index buffer, which takes the command buffer, the index buffer, and an initial offset of 0. And finally a vk index type uint32. The index type
Anyway, let's if has index buffer. Copy this. Index buffer. One buffer index buffer 0. Index buffer 0 1.
type of the indices vector. For
VK index UN 32. Yeah,
You can save memory by using a smaller index type. A 16-bit index can store models up to 65,535 vertices, but more complex models may have significantly more vertices. So I've chosen to just stick with using a 32-bit index type for the tutorial series to keep things straightforward and model independent. Before we can test this code, we need to update the createCube model function in the app implementation to now use the builder constructor. At the top of the function,
first tab, let's go to that. First tab, CPP. There it is.
the model builder variable named model builder, and then change the line below to set model builder.vertices to equal our vector.
Yeah. Now we model builder, model builder, empty brackets. Leave it all that. Model dot. How do I fix this? Um, model builder, not vertices, model builder dot vertices. Okay. I'm missing something here. Control C, Control V.
And then update the model constructor to take the builder object as its second argument. Build and
Now we're just taking the entire model.
things are working as they were previously, so the vertex buffer functionality still works. Next, we need to test out the index buffer.
Okay, let's play, test everything. Hmm. Yeah, let's reload it. Okay. Yeah, the camera angles is all working correctly.
Provided an updated createCube model function in a pastebin link in the description below that uses indices to specify the vertex ordering. I will remove the old
Yes, then let's go down. Uh, 326 actually. Okay, minor differences. Oh yeah, I was looking for the paste bin. Okay, Q model. Control C. Control C. Yes. I've set everything now. Yeah, this is when copied. Let's go back.
Old function and overwrite it with the new implementation. The first thing to notice is that we now have only 4 vertices specified per face as opposed to 6, as well as a vector of index values specifying which vertex values are used for each triangle. We still require 4 vertices per face, since each face has a different color. However, if the cube was just one color, then we would be able to further simplify the vertex data to just 8 vertices. Build and run your code to confirm everything is still working correctly. The cube is now being rendered using an index buffer. Note that if you try to measure the performance, you won't likely see any change. With such a simple scene, memory access won't be the bottleneck for performance. Since we've already
Okay, let's test if it builds. Yeah, it's loading. It seems to have loaded. Let's test. Yeah, the user input still working. Yeah,
now is as good a time as any to further optimize our models. Currently, the memory type we are using to store the vertex and index buffers isn't as optimal as it could be. For both these buffers, we have been using the host visible and host coherent memory bits. Looking at the official Vulkan documentation, we can see
okay,
that
now
host
we're
visible
getting
bit specifies
into staging buffers. Wonder what this
that
is.
memory allocated with this type can be mapped for host access using VK-map memory. What this essentially means is that the host, aka the code on our CPU, can write to this memory. However, the most optimal and fastest memory requires the device local bit to be set, and is typically not compatible with the host visible bit. In order to use device local memory, we must first copy the buffer data from the host to a temporary buffer that is visible to the host. From there, we can then copy the data to device local memory by using the vk command copy buffer function. Once this command has copied the data, we can destroy the temporary buffer. The temporary buffer used
One sec.
can write to this memory. However, the most this we've already
Let's go back.
been working in the model class. I think now is as good a time as any to further optimize our models. Currently, the memory type we are using to store the vertex and index buffers isn't as optimal as it could be. For both these buffers, we have been with the host visible bit. In order to use device local memory, we must first copy the buffer data from the host to a temporary buffer that is visible to the host. From there, we can then copy the data to device local memory by using the vk command copy buffer function. Once this command
Oh. I wonder if this is possible in like newer versions. I feel like unless there's some like security concerns, which like makes sense. But there should be an option to just copy directly here, right?
has copied the data, we can destroy the temporary buffer. The temporary buffer used in this process is commonly known as a staging buffer. Okay, so back in the model implementation, let's update both the create vertex and create index buffer functions to first stage the buffer data and then copy it to device local memory. Underneath the line declaring the buffer size, I'll add 2 new local variables. One with type vk buffer called
Vertex buffer. Yeah. a vertex buffer, we'll be adding it after the vertex count. VK buffer staging buffer. Just leave it empty.
Staging buffer memory. We need to create two buffers, one for the
VK buffer staging buffer memory. Okay, let's see what's
another for the staging
next.
buffer. So copy the create buffer command and paste it in below the code for mapping the host to device memory. Let's update this first create buffer command to instead create the staging buffer. The buffer size remains the same, but we need to update the buffer usage to now be vk buffer usage transfer source bit. What this does is tell
Copy paste this. VK buffer usage transfer source bit. I'm guessing this will be the transfer destination bit. Transfer destination bit. I'm assuming.
you're creating is going to be used just as the source location for a memory transfer operation. Next, the staging buffer needs to be host visible, and host coherent tells Vulkan that whenever we update memory on the host side, to automatically flush that data to the device side. Finally, change vertex buffer and vertex buffer memory to instead be staging buffer.
Yeah, the staging buffer. Staging buffer. And this is device memory. Having the arrows just show right next to it is so handy. Even if the hint is not correct, it'll at least tell you that this line is the error. So handy. I don't know why it's not like a built-in feature, honestly.
Now we need to create the host mapped memory region with our staging buffer. So update vk map memory and vk unmapped memory to use the staging buffer memory variable. Okay, for creating the vertex buffer, we need to
Staging again stage.
that can be used as a transfer destination. So following the usage vertex buffer bit, add the pipe operator, then vk buffer usage transfer dst bit. For the vertex buffer,
VK buffer vertex changes to vertex. Okay.
optimal device local memory. So we need to remove both the host visible and host coherent bits, replacing them with
Property device local bit delete.
vk memory property device local bit. Next, we need to tell Vulkan to perform a copy operation to move the contents of the staging buffer to the vertex buffer. The device class I provided already includes a helper function to do just this. Add lve device.copyBuffer with the staging buffer as the source, the vertex buffer as the destination.
LV device copy buffer, staging buffer, staging buffer memory.
Bytes to copy. And that's it. All
Vertex buffer and then buffer size. Let's close this. Now that's all correct.
buffer as it is no longer needed. I am going to copy and paste these 2 lines from the destructor into the end of my create vertex buffer function, and update the values to be vk destroy buffer staging buffer and vk free memory staging buffer memory.
Destroy the staging data. Staging address.
Virtually the same. I will copy from the declaration of staging buffer down to its destruction, and then in the create index buffers function, just under
Okay, staging buffer. Yeah.
function, just under the buffer size declaration, replace the remaining contents of the function with what we've just copied. Okay, so stage
Okay, from here to here. Yes. Index. And this is buffer size, index width, index buffer bit, index control C, control. Okay, staging index buffer, staging buffer memory. Any other thing with vertices or vertex? No.
and staging buffer memory are all good. Creating the staging buffer doesn't need to change. For memcopy, we need to copy the indices rather than the vertices.data. And then in create buffer, we need to update the buffer usage from vertex buffer bit to index buffer bit, and then change the last 2 arguments to be index buffer and index buffer memory. Finally, in the copy buffer command, change the destination argument to be the index buffer. And that's it. Build and run and things should work just as before, but we are now using more optimal device memory. This can make a noticeable difference after we start working with more complex models. So when should you use a staging buffer and device local memory? Well, it works best for data that is static, so 3D meshes are a good option. If you find yourself frequently updating the contents of the data from the host, then the extra step of having to copy the data from host visible to device local memory may actually negate any performance gains. Furthermore, the implementation I provided for the copy buffer function in the device class relies on a single time command.
Okay, let's test it out. Make sure there are no errors. Okay, look up, look down, go down. Should also change the key binding for this. I think it should have been Q E to go up and Q to go down. Shift E, Shift Q. Save and load. Hmm. Yeah, this new key key binding is much better. It's more similar to what is already used in other game engines. Yeah, yes.
Be idle to ensure that the copy command has finished before we start rendering. This can be avoided with the use of a memory barrier, but that is beyond the scope of this video. So for now, I recommend only using staging buffers for static data that is loaded at the start of the application. Anyway, that's it for today. Thanks for watching, and keep on coding. Cheers.
Let's just go through the comments.
Welcome back. In this video, we're going to move past. Currently, we pass in each vertex for every triangle that makes up a 3D mesh. However, most vertices in a mesh will.
Let's see if anything important is mentioned in the comments. Okay, this is just about renaming. Okay, when you rotate the cube and use as always, I'm looking forward to the next video. At Vulkan tutorial, they use hash function to get rid of duplicate vertex points and vertices. This is a fine way to reduce count. Manually created index list seems harder to make, or do model builders do that for you? I guess there is software to make models. By doing the same method as a welcome tutorial, we build the index list as we do. So we filter out the duplicate vertices using the hash function. Definitely GPU doing the processing of vertices and fragments. Uh, yes, this is an excellent summary of what we're doing. It's possible when creating the buffer objects to use different types of memory based on the memory property flags. So does the compile program get uploaded into the GPU's VRAM, or is it's locally located in the main RAM? When we call create graphics pipeline, the create info has the shader data, and part of that process would be moving the compile shader data to the GPU VRAM. uniform buffers, how to build for Android. I haven't tried working on Android yet. We also have to not use JLFW, I believe. I think I'd like to cover all the basics first. Okay. I don't think we'd get to this one today, but while I
Welcome back. In this video, we're going to move past the simple.
Okay, let's save all of this. Met and push all of it. Okay. Let's play a bit of chess just to like wake me up a bit. And then we'll go on to the next tutorial. Right, and why does it keep selecting one or the other? Okay, this is trying to do some gambit type of thing. Let's see. I'll just bring this here. Okay, we can pin the knight. Can I just get rid of this if we can. Should we take it? Let's just develop our pieces. Yeah, just like wasted move. Okay, can't move. Uh, my mistake. Let's just bring this out. Take this. Hmm. Let's throw on a check. Okay. Hmm. Let's castle this way. Let's attack this. Yeah. Are they up in pieces? No. There's up one. Let's bring this here and then bring this here. Mm, let's pick this out. Let's run this here. Hmm. Let's clean up the board some more. Let's go here. Let's take this. Push this. Check. Hmm. Let's push this. Like that. Hmm. Let's go for this. Like this. Yeah. Hmm. Let's bring this forward. Let's see if I can get the queen first. Like that. Yeah, let's clean up the board a bit. Hmm. Yeah. 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 Last. Sure, there must have been a bunch of mistakes, but whatever.
Simple 3D cube and extend the model class to be able to read in model
Let's
data using the
start
wave front object
working on this one now.
file format. Up until this point, we've hard-coded our model data directly into our code. This is time-consuming, inflexible, and prone to errors. It would be much better if we could specify all model data in a separate file that could be loaded in at runtime. The wavefront object file format is an open geometry definition file supported by most 3D modeling programs. A V indicates a vertex position, Vn indicates a vertex normal, and Vt a texture coordinate, with the subsequent values being the x, y, and z component values. So for example, the wavefront object file for the cube we've been rendering in the previous tutorials may look something like this. The first 8 values specify the 8 vertex positions, one for each corner of the cube. Then we have 14 texture coordinate values. These indicate how a 2D image would get mapped to cover the surface geometry of the model. And finally, 6 normal values, one for each face of the cube. I will explain in more detail in the upcoming tutorials the purpose and use of vertex normals and texture coordinates. The final portion of this file format that we care about lists how to construct each individual face, which for our rendering pipeline will all be triangles. Each face of the model will be listed on a separate line that starts with the letter F, and will consist of 3 face elements, one for each vertex of the first. We want to use the 5th vertex position value. Then following the forward slash, the next value is an index into the texture coordinate list. So the first texture coordinate value, and then, as you can probably guess, that leaves the last value of the face vertex of our triangle is do the same for the other 2 face elements, the full file format specification. For more write our own code to read in this file format, we will make use of Tiny Object Loader, a single file wavefront object loader written in C++. So let's start by adding Tiny Object Loader to the project. Follow the link in the description below to navigate to the Git repo for Tiny Object Loader. You can download the entire master branch, but really all we need is this single header file. In my development folder, I have a directory called libs, and I will create a new folder called Tiny Object Loader. Then back on GitHub, I'll open the raw version of the file and save it to the Tiny Object Loader directory I just created. When saving the file, make sure you don't accidentally include an extra file extension, such as txt. Next, we need to include Tiny Object Loader to be built with the rest of our project. How you do this will differ depending on how you build your project. I am using a makefile, so I first need to add the path to the directory I just created into my .env file. So tiny object path is equal to users Brendan dev libs tiny object loader.
Okay, let's go to GitHub for this. It just has like all the code in it, I guess. Let's go here. Let's go to my CMake. GitHub. Git repository. Let me just make sure.
Then in my make file, I will add the tiny object path to be included in with the C flags, and that's it. One other thing you might want to do is if you're using VS Code is add this to the include path of your C cpp properties.json file. This way the code completion will work correctly within the VS Code editor. Setup for Visual Studio on Windows is pretty similar. Create a folder in your libraries directory called tiny object loader, and then save in it the tinyobjectloader.h file. Then in Visual Studio, navigate to project properties, and in the C++ settings underneath in the general heading, we can add the path to tiny object loader.
I'll just do it like this. Let actually make it. External libraries. Make available any object loader. Control F. Control V. Gets running it now. Match content make available. What if I just want the one text file? Let's see, git repository. Let's try this. Not found. Yeah. Hmm. Yeah, download it.
To additional include directories. So click Edit and add a new entry inputting the folder's path. Now let's quickly test that we've included TinyObjectLoader correctly before progressing with the rest of the tutorial. Open the model implementation file, and near the top, first define tinyObjectLoader_implementation. You only want to have this defined in a single CPP file within the entire project. The define signals to the preprocessor that this file in the project will contain the implementation for TinyObjectLoader. Then include
Let's do a rebuild. CMake error, fail to check out lost. And let's do this. And let's also open up the file. Open Explorer. CMake will dialog dependencies. Let's delete that. Let's rebuild it now. So we wanted to build fetch content. Let's see. CMake fetch content declare. Find package fetch content. Let's say URL. Let's get the raw page. Not this. Tiny object loaders from 2017. Hmm. Yeah. Hmm. So open a raw version of the page. Okay, let's try again. Problem with okay, read open. Yeah, that's only for like compressed files. It can't just get a normal file. Yeah. Let's rerun it. Hmm. Let's see. Oh, this will be useful. And CMake or do fetch content declare a single file from get repo. Forward load node. Hash includes fetch content. Let's check the Vulkan page. load in models. So we will use tiny object loader. Make file. Does it like have to be added as Control C fix? Get tags. Let's try this. Control C. Yes. Let's load it and see. That worked. Why? Why did the other ones not require this? Yes, by default it's master. Perhaps. Yeah, default for the place is master. That's why it was breaking. Okay. Glad it was a simple fix. Let's just rebuild it. Let me do a proper rebuild. Clone is already closed, so it's just generating. Okay, cool. Now let's test if it works.
tinyobjectloader.h in angle brackets, and you can build
Let's zoom back in.
of the tutorial. In the general head directory, included tinyObjectLoader correctly before progressing with the rest of the tutorial. Open the model implementation file, and near the top, first define tinyObject.
Early model implementation. Custom view. Libraries. Hash define.
Defined in a single CPP file within the entire project. The defined signals to the preprocessor that this file in the project will contain
Tiny object loader. Dash implementation.
loader. Then include tinyObjectLoader.h in angle brackets, and you can build
Hash define. Hash include. Tiny object loader.h. I did add it correctly, right? And here cannot find
things are still working. That means tinyObjectLoader has been successfully added. Finally, I've provided some model files to get started.
I'll just see hash include 0. Dependencies. Did it not load anything into that folder? Open an explorer. Hmm. It did not download anything. My gosh. That's why there were no build errors. Git release. Version 1.06. Let's try this. Yes, this file. It's updated 6 months ago. Somehow. Okay, let's build it. Build with C++ features, auto detection. Hmm. Later, rebuild it. Fail to get the hash for head. Let me save it and rebuild it. Hmm. Load tiny object loader using CMake. Should I just create a fork and delete everything but after log? Let's log in with Google. I'll be right back. And let's focus and then delete everything else. Copy the release branch only. Just header file of tiny obj load. Let's see if this works. How do I edit this? Is there any way to like edit it from me? Hmm. Let me just clean up my system. GitHub custom. Say let's clone out tiny object. Okay, making Vulkan stuff. I'll just keep it in this folder. Clone. For my own purposes, can not show an explorer and just delete all these other things. Delete. The readme should be somewhere. Delete all extra files. Okay, let's push it. Now let's load it. Or copy it. Paste. Rename. Over here. Let's see, what is it called for this? The master, yeah. Let's make it GitHub. Origin. Hmm. Yeah. Now let's try seeing if it builds. Okay, it did build as a source. Nice. Inside it has it. Yeah. Now let's hit layer. Make sure that all is working. Build fail. Where did it fail? First step CPP. Let's try this. Why is it not working? Cannot find any object file in search paths. Dash include. Why is it not included? Am I missing something here? GLFW, Control F. Let's see. Target include. Like if I put it before. Build. It was finished there. Is this supposed to be like HPPP? No. CMake build debug source. Tiny object loader. Hmm. Let's see. Seems to only be checking the dependencies for GLFW and GLN. Why is it not checking for this? Hmm. Does it have to be the same middle? Uh, Would this work? Build files have been written. Just hit run and see. Control C. I'll just run it like this. See if there are any problems. Cannot find alt any file builder. Is JetBrains doing something? Settings. Library. Step in advanced settings. Let's see, maybe it's the include directory part that is an issue. Add dependencies. Mhm. They each have their own build sorts. Maybe that's why. GLM build is a hmm. Mhm. Hmm. So make a single file as a dependency. Target linked dependencies. Hmm. Target linked libraries. Target include directories, about now. Hmm. Open an Explorer. I think there has to be like a CMake thing for the project itself. CMake list.txt. Uh, let's see, GitHub. the cycle restore. Let's see if it's come back. Okay. Okay, I got the CMake list. Let's clean up. CMake project. Let's clean this up. Delete that. Find packages, sanitizer, permeate this. Sort library, library name, project name. Okay, we're not doing any examples. Source. Example source. I don't need any of these. Elf tiny object with Python. Add sanitizer. Elf build shared library. Hmm. Alright, let's delete this. Delete this. Config file. Installation. Let's Keep things simple. Sanitizers not required. Let's bring this to the side. Set target properties. Install, build. Include directories. Interface, build interface. And let me upload these changes to GitHub. Format one. Set library name. And last commit. Sure. Let's see if this version works better. Otherwise, I always could just add it directly. Let's refresh. Same. Source dependencies. We'll get all of these. Now rebuild it. Now it's not even like getting it correctly. Build. Let's see what happens. Control X. Build. Hmm. Keyboard controller. What is this? It's not even like getting it correctly anymore. Let me close and restart CLI. Say scenic add tiny object loader. Here's fetch content. And build using fetch content. Hmm. Let's go back to the original. Hmm. Let's see. Cloning a branch is already active, already on release, configuring done, generating build files have been written. Okay, any object loader, build files. Hmm. Let's see. Makes a build, but does not glw build source. Scenic files, docs. Include tiny object. Okay, it's working. Hash define as the text.
Successfully added. Things are still working. That means time.
Yeah, it's working now. What? Let's run it and see. Let everything load. Okay, it's working. Why was this such an issue? Okay, I guess switching it on and off work. Well, let me save this. Import any object loader from CMake. Oh, this was so annoying. Just had to switch it on and off. Whatever. Okay, now let's not worry about that anymore.
Finally, I've provided some model files to get started with. Follow the link to my Google Drive, open the models folder, and click download all.
Okay, model should have. Yeah, can close all of these. Or this one can be deleted. Okay. That was so much nonsense to deal with. Vulkan stuff. Yeah. Reload. And let's download the models. Download. Hmm.
Unzip the folder and copy it to your project directory. Okay, let's get to coding.
Okay, you just directly copying it. Okay. Uh, okay, let's unzip this package. Extract. Let's bring it in. Okay.
Model header and extend the vertex struct to also support normals and texture coordinates. Add a field of type GLM vec3 called norm.
Model header. GLM vec3 normal.
Vec2 called UV. UVs is just another commonly
GLM vector UV. Keep it empty.
texture coordinates.
Yes.
Inside the builder struct, I'm going to declare a void load models function that takes a const std string reference called file name as the argument.
Void std equal to void load model
To create a unique pointer model object. So first include the memory header, then inside the model class, declare a static function
should include memory
of LVE model type called create model from file. And this will take an LVE device reference called device and a const std string reference called file path.
Okay, it's above this. Static std unique pointer LV model create model from file LV device function device const std string file path. Yeah.
Declaration and head on over to the model implementation file. I will paste
Choose above file. One second. Want to at least finish this one properly.
add my class name scope and remove the static keyword.
All the model function shift 6. Oh, okay,
I'll initialize a variable of type builder called builder. Next, call the builder.loadModel function, passing through
make it empty.
and then return std make unique of type LVE model with arguments device and builder. I'm going to include IOStream.
I should load Livestream.
Vertices.size. This way, for now, we will be able to see how many
Studies out. Model load mastery and vertex count. Okay.
contains. Next, we need to implement the load model function. So at the bottom of my file, but still within the namespace, I will add void LVE model builder load model. With the argument const std string reference file path.
Void the model builder load model. Yep.
Tiny object : attrib t called attrib. Next, an std vector with type tiny object shape t called shapes.
And let's see. Tiny object. 1 second. 1 second. I'm back. A good thing I close that.
Then another vector but with type material t called materials. And finally declare two std strings called worn and air. All of these values will be set by tiny object loader and will store the results of
Attrib t attrib std vector tiny object shape t shapes std vector tiny object materials and std string std string arrow.
file. So in an if statement, we will have not tiny object load object with the arguments reference to attrib, reference to shapes, reference to materials, reference to worn and error, and finally file path.cstring, which provides a car pointer representation of the string variable. If we fail to load the object, we'll throw an std runtime error with worn plus error as the output. So following this load object,
And if tiny object load object and some attribute dimension shapes, some materials, one arrow of alpha dot c string. One time arrow, one plus arrow. One plus arrow.
We declared should now be initialized with the data from the .obj file. The trib variable stores the position, color, normal, and texture coordinate data. The shapes variable contains the index values for each face element, and the materials we will ignore for now and leave to a future tutorial. Okay, so we've got our data. First, let's call vertices.clear and indices.clear to start from a fresh builder state.
Vertices dot clear, indices dot clear.
Auto reference shape in shapes, followed by a second for loop with const auto reference index in shape.mesh.indices. This loops through each face element in the model, getting the index values. Inside the for loops, declare and initialize a vertex local variable. Let's start by setting the vertex's position field. To do so, we should first check if index.vertex index is greater than or equal to 0. The vertex index
For const auto, for const auto and index shapes dot mesh dot indices. Shape
says what position
vertex of index not vertex index greater than or equal to 0. Vertex color vertex normal vertex series.
use. Index values are optional.
Variable vertex can be moved to an scope.
That no index was provided. If a vertex index is provided, then we can set the vertex.position equal to curly brackets attrib.vertices at an index of 3 times index.vertex index plus 0. Each vertex has 3
Let's keep it out for now.
values that are tightly packed into the attrib.vertices. Right,
Plus
so
0.
to read the corresponding position, we need to multiply by 3 and then add 0 for the initial component. Then duplicate this line twice, updating plus 0 to plus 1 and plus 0 to plus 2 for the positions y and z components respectively. Now reading the normals and texture coordinates is all very similar.
Plus 0. Let's see. Control V. So
block and paste it just below. Change each occurrence from vertex index to normal index, vertex.position to vertex.normal, and attrib.vertices to attrib.normals. And repeat this one more time for the texture coordinates. Change each occurrence of normal index to text chord index, attrib.normals to attrib.text chords, and vertex.normal to vertex.uv. The only other notable difference is that the UVs are 2 components rather than 3. So remove the last component and change to using 2 times index.text chord index. And then we can add this vertex to the builder's list of vertices with vertices.pushback.
I'm not using color. Let's search.
And that would be pretty much it, except
Vertices get still inside the if condition. Vertices dot pushback vertex.
colors yet, and that is because the wavefront object file format doesn't actually support them. However, there does exist an unofficial extension that is supported by Tiny Object Loader. Some applications support vertex colors by putting red, green, and blue values after the X, Y, and Z vertex position components. I've included a colored cube object file to demonstrate this feature. So inside the if block for vertex index, we can extend it to add color support. First, I'm going to calculate the last color component's index value and store it in auto color index is equal to 3 times index.vertexindex plus 2. Then check if color index is less than attrib.colors.size. We use the last index because color attributes are optional, and this is a convenient way to check that a color has
Auto color index equals 3 star index dot vertex index plus 2. I could just go 3, 4, 5. Color index.
and the index is in bounds. If this is true,
Okay, that was what was confusing me extra. And,
then we can initialize the vertex.color field. This is pretty much what we had before, except each component is equal to attrib.colors rather than attrib.vertices, and rather than plus 0, 1, and 2, we instead have color index -2, -1, and -0.
oh, what minus? -0, -1, -2.
Finally, add an
Strange.
else statement setting the vertex color to some default value if no color has been provided.
Let's vertex color is white. Of color index attribute colors dot size. Else. Cut. Paste. Yes. Okay.
All that's left to do is load in a model and render it. Open the app implementation file, and we can get rid of the create cube model function. Game objects, change create cube model to file, passing in the device and model/colorcube.obj. Note that this is a relative
Now we model, create model from file, movie device, colored, cube. Hash define model.
If you run into an error, try using an absolute file path instead. For example, this is what I use on my Windows machine. Build and run your code, and we get a rainbow colored cube. That's because each vertex only specifies one color, and then the fragment color is interpolated across.
Let's attempt to. Let's see if it runs. I failed. Cannot open models file. Cannot get added. Hmm. Has it not been added to the build or something? No, worked. Yeah. Let's see the CMake list. Shader sources. Add custom target. Project name, shadows. Models. Let's try this. See if it works. Let's see. Simulate binary directory. Looks like I might have to give a custom file. Where's the build? Shadows. So for which models $sign model sources. And custom target. Let's make one. Senior just this for loop to copy all the models obj models to a folder called models. Okay, make directory. Create target project possible copy of different models. You make runtime output directory models file name. And that's kind of implicit. Let's see if this works. Now target Vulkan loading has been created in this directory. Project name, hash models. File make directory. Hmm. So it depends on sudo. Object. Hmm. Okay, x64 debug. Let's leave it. Already spent too much time on this. Modules. Looking at this. Yeah. Let's see if this works now. Okay, it's working. Okay, and let's at last.
Triangle, just like in tutorial 7. If we wanted a model to look like the previous 6-colored cube we had, we would need to duplicate each vertex position twice so that we could specify a different color per face. Now let's try a more complex model. Update the file path to load the smooth vase object file.
Smooth is
This appears kind of small, so I'm going to change the transform.scale to equal glm back 3 with a multiplier of 3. And I will also rename the cube local variable to be GameObject, as that's a bit more applicable now. And there we go.
game object model 6 game object. I just play it normally. Let's change this to 1. And see.
with a multiplier.
Okay, I just need over 3. GLM 3. Okay. Close.
And I will also rename the cube local variable to be game object, as that's a bit more applicable now. And there we go, we have a nice white vase with a
6.
888. However, even with so many vertices, you can't really see anything because the entire object is just painted white. To get something with visible detail, we need to apply lighting, which we'll do so in next week's tutorial. So we've successfully loaded in a model using just vertices, but we didn't make use of the index buffer that we added just back in the previous tutorial. Index buffers are a great optimization for reducing the memory required to store complex 3D models, so we definitely want to be able to use them when loading objects from a file. But one thing you probably noticed is that each face element definition can use a different index value for the position, texture coordinate, and normal. But in Vulkan, we can't do this. We can only have a single index buffer, and we need all the values that make up each vertex to be grouped together. So creating an index buffer isn't quite as straightforward as just reading in the face element's index values. The purpose of an index buffer is to avoid having any duplicate vertices within the vertex buffer. As each face element is processed, we need to come up with a way to detect if we've encountered this vertex value before. If the vertex is new, we add it to the vertex buffer and add its position in the list to the index buffer. If the vertex already exists, then we can discard it and add the index of the existing vertex into the index buffer. Once every face element has been visited, we will be left with a list of unique vertices, and a list of index values pointing into the vertex list indicating how to construct each triangle that makes up our object. This method I have just explained is the exact method provided by vulkantutorial.com. So if you found my explanation hard to follow, check out the loading models tutorial linked in the description below. To quickly be able to check if a vertex is new or has been seen before, we will use an std unordered map, which requires we provide a hash function that can take all the data in our vertex struct and map it to a single fixed size value. The unordered map can then use this hash value as the key to look up the vertex's position in the list of vertices. So first let's create a new file called lveutils.hpp. I've included this function in the paste bin link below. This is a function that can combine
lveutils HPPP. New header file. lveutils. Hash components. Space away. Template. Type name. P. Type name. Dot. Rest. Word. Hash combine. std. std size. Size and seed.
hash functions are kind of a complex.
Note I forgot to include. Has given it to me again. Yeah. Still, what is this function?
Complex topic, and I assume most of you guys are already familiar with how unordered maps work, so I'm not going to delve into the details of why this will work well. It's based on a Stack Overflow answer in the link provided. Note that it makes use of fold expressions, which is a C++ 17 feature. Okay, now in the model header, we need to overload the equality operator for the vertex struct. So
Okay, I have to definitely look into this. C++ dot. Operation. Let's try this. C++ OX adds hash. Cleanest way to implement something like this. Template class T and learn void hash combine. Size seed. Constants T and V. What is this rest then? Sure. As the seed over is bit shifted by 6 and 0 is the algorithm used by Boost. What is this? Yeah. Seed Q hash. From QTM. But let's see. Explain.
operator == const vertex reference called.
Anyway, that's working. Let's go to this. Bool creator constant x. Return equals position, color, normal, UV. Called hash combine that combines multiple hash values into a single hash value. It's commonly used to create a composite hash for multiple values, which is useful when you need a hash for complex object-based term. It's member variables. It accepts one or more types. A reference to the hash value that will be modified. The value is to be a hash where v is the first value, and the rest is parameter pack of the remaining. Magic number that helps in producing a good distribution of hash values, help mix the bits of the current seed, combine the new hash with the existing seed. Course of call. Yeah.
Mark the function const, and then we simply check that all the struct fields are equal. So position equals other.position, color equals other.color, normal equals other.normal, and uv equals other.uv. Then in the model implementation, scroll to the top and include lveutils.hpp. In addition to the equality operator, we need to implement a hash.
Hash include libraries. Hash include utils. HTTP.
For the vertex struct, which will make use of the hash combine function we just wrote, but to hash the individual GLM back component.
The utils. Whatever.
This functionality is technically experimental and subject to change, so we first need to define GLM enable experimental. But in practice, the GLM
Hashtag.
also, I don't think this is something to really worry about. Then include GLM GTX hash.hpp. Finally, we also need to
Hash include GLM GTX hash.hpp. Let's check if it's still experimental. Is experimental. Even on the latest one. Yeah, it's still considered experimental. Yeah.
include unordered map. I am going to inject a hash function for the vertex struct into the st.
Hash include unordered map.
Namespace. So just following the include statements, but outside the LVE namespace, I will add namespace std followed by template angle brackets. Next, we declare a struct called hash with type LVE model vertex.
Namespace std template struct hash we model vertex.
Function call operator. So we have return type size t, then operator brackets, and as the operator function calls argument, we have an LVE model vertex const reference.
St operator only model vertex construct X.
and also mark the function as const.
Summary operator
A type size t called seed equal to 0. This will store the final hash value. Then call lv with the arguments seed, vertex.position, vertex.color, vertex.normal, and vertex.uv, and then finally return seed. With this, we can now take an instance of the vertex struct and hash it to a single value of type size t, which can then be used by an unordered map as the key. Okay, scroll down, and in the load model function, let's initialize an empty std unordered map, using vertex as the key type and a uint32t as the value type. And I'll call it unique vertex.
and load model. There we go. I was adding a chat about
We'll keep track of the vertices which have already been added to the builder.vertices vector and store the position at which the vertex was originally added. Then scroll down to the end of the function, but still inside the for loops, and replace vertices.pushback with if unique vertices.count of vertex is
if we need vertices
then unique vertices at vertex is equal to static cast uint32 type of vertices.size. Then also call vertices.pushback vertex. So what this does is if the vertex is new, we add it to the unique vertices.
vertices pushback vertex.
Its position within the builder's vertices vector is given by the vertices vector's current size. Finally, after the if block, call indices.pushback unique vertices at vertex. With this, we add the position of the vertex to the builder's indices vector. And that's it. We can build, run, and see our base object once more. The big difference is that the vertex count has been reduced from 30,888 to just 5,545.
Yeah, that's simply okay, 5,545. Feel like some stuff got messed up compared to before. But on his it was just completely white, so I don't know exactly what's going on. I'll figure that out tomorrow. Let me just check the comments.
Index buffer, we're saving a lot of GPU memory. As a final step, let's clean up IOStream and remove the print statement.
Stream.
I would like to mention that we have share code, get
Appreciate the work you've put into this. This will 1,000. What was zero? Tiny object loader implementation. Oh, was I making that mistake as well? Don't even know.
Feedback, and meet like-minded people who are also crazy enough to try and make their own game engine. So if that is something you would like to join, links in the
So let's save all of this. Okay, 17. Loading 3D models. All of them commit and push. Oh, yeah. Let me update the titles and loading. Loading 3D models. Okay, has been pushed. Nice. Okay, it's quite late.